Sit over there and I'll just put small signs up for 5 minutes,
Sure.
2 minutes.
Yes.
Yeah?
Yes, and there is no other mic, right? So I need to speak here, right?
I think so, yeah.
Okay.
Unless,
Okay.
yeah.
No,
I
that's
guess you
fine.
could also tank, but this is probably more comfortable.
Yeah,
right?
that's fine, yeah. So it's a 12 minutes talk, right? Or
It's,
10 plus
I guess it's 10 minutes plus 2 minutes questions.
Okay.
Yeah. So I'll give you kind of the signs for the 10
Sure.
minutes. And
Yeah.
So yeah, I think we can get started.
Should start?
Okay, welcome everyone to this morning's session on graphs and clustering. It's a relatively short session. We have 5 talks, and we'll start with the talk by Barna on learning partitions with optimal query and round complexities.
Okay, thank you everyone. So this is a joint work with Hadley Black and Arya Mazumdar. So Hadley is the postdoc at UCSD. He was supposed to give the talk, but he couldn't come here, so I'm giving the talk. Okay, so clustering probably doesn't need a motivation to this audience. Like and in clustering, you want to group data based on similarity. So what we are going to talk here is about clustering with an oracle or clustering via crowdsourcing, because here you can assume that you have an oracle and you can ask some questions to the oracle to help you in clustering. And this oracle you can think about is like these answers to the queries are given by crowd workers or experts and whatever. So that's like why this oracle sometimes you can think about clustering with an oracle is clustering via crowdsourcing. So can you offload the work of computing a clustering by asking simple questions to external individuals? And of course your queries have to be simple if a human being have to answer those questions. And an example of the simple possible query is this pairwise same cluster queries, where you ask whether 2 points in your data set, they belong to the same cluster or not. Okay, and the motivation is like these kind of queries, these are easier for human to answer than by machines. So for example, here you are asking whether these 2 pictures of animals, these animals belong to the same genus or not. And here the answer is yes. And in this case, the answer is no. So you can ask this kind of simple pairwise questions, and the answer will be either yes or no. And the question is, how can you use this kind of pairwise queries minimally to help you in clustering? This problem, this has been really well studied for quite a few years now. So more formally, what is the problem statement? So you say you have n elements, you have a set U of n elements, and there are some hidden k partitions. So there are k clusters which are hidden. Of course, you don't know them. And you want to recover them exactly by using this kind of pairwise queries, yes or no. Like you can ask given to any 2 points whether they belong to the same cluster or not. And the answer will be yes or no. So you can, the goal is to minimize the number of queries and recover this hidden partition. So the wish list, first of all, is query complexity. So you want to minimize the number of queries because every query, if you're asking a crowd worker, you have to pay for it. So you want to minimize your payment. The another one is round complexity. So round complexity is like in how many batches you want to make these queries. So if you think about, like again, you are asking crowd workers, so this helps to parallelize the queries, because each round of queries might take some time. If you have more rounds of queries, that will just add to your time complexity. So responses may be slow, so it's important to parallelize queries as much as possible. So that's your round complexity. So another thing, like here I was talking about pairwise queries, but you might want to say like, okay, so pairwise query is very simple, so maybe we can allow some little like complex queries. And one complex query could be like, instead of giving 2 pictures, you give a subset of pictures and ask how many clusters are there in the subset. So yes/no queries for two images is like saying whether two images belong to the same cluster or not. Instead, you might give like 3 images and say, hey, how many clusters are there in these 3 images? So these are subset queries, but obviously you don't want these subsets to be large, because then again, it will be difficult for a human to answer those queries. Okay, so these are kind of the wish list. We want to minimize query complexity. We want to minimize round complexity. We might be able to handle little larger subset queries, but the subset size should be small as well. So once again, so this is our formal statement. Set U of n points, hidden partition. We can query whether x, y are in the same cluster or not. And the question is, how many queries do we need to learn this C1 to Ck? This problem has been well studied, say from 2015 onward, like more theoretically. And there is a very simple order of nk query algorithm. This is an adaptive algorithm since it requires k rounds of queries. Okay? And if you only want to allow 1 round of query, there is a lower bound which says you cannot do anything better than n squared. And n squared is trivial. N squared means like n is the number of points, so you can ask every pair queries, you get the yes/no answers, and then you can just partition based on the yes/no answers, right? So n squared is trivial, and it says that if you only require 1 round, like non-adaptive, just 1 round of queries, you cannot do anything better than n squared. But if you allow k rounds, you can do it in nk query complexity. And this problem is from theory, it has been studied in the last 10 years. But if you go back and if you look at where the problem originated, as far as I know, it originated in the database community where they tried to use crowdsourced platforms like AWS to help in clustering. And in those communities, this problem was introduced back in 2011, 2012. Okay, and this nk query complexity for adaptive algorithms, this is actually tight. So you can show lower bound as well, and which holds for both deterministic and randomized algorithm that this nk is tight. And this is a very simple, algorithm-wise, it's very simple. So you just take 1 point, like say this red point, then you ask all possible n queries from every other points, and that tells you, so maybe these 2 points belong to the same cluster as this red one, so you color them red, so that's your n queries. After that, you take another point, so maybe this one, and then you ask another set of all n queries, and that gives you that these 2 points belong to the same cluster, so that gives you another n. So basically, you are finding one representative point from each cluster. So there are k clusters. For each representative, you are asking n queries, and that gives you nk. Okay, so that's very simple nk algorithm. But the catch is that this requires k minus 1 rounds of adaptivity. So at every point, like you kind of have one representation from one cluster, making n queries, you know everything in that cluster, then in the next round, you find another representation from the next cluster, and so on. So can we do better? So the question is, okay, so nk is optimum. Now can we achieve these nk queries without requiring k rounds? And another question that you might ask, that if I give you a budget of r rounds, what is the best query complexity that you can achieve? Okay, so result-wise, what do we have? So we show that if you are given a budget of r rounds, this is the query complexity that we achieve. It's slightly difficult to sparse, but the takeaway point is like, you require only log n rounds to achieve the query complexity of nk. So instead of k rounds, you just require log n rounds. So if k is large, like some n to the, say, 0.001, whatever, right, some constant, then you have a double exponential improvement in the round complexity. So that's kind of the first thing. And if I have to if I have to tell you a little bit about the algorithm is like pretty intuitive. So for example, like if you're considering r equal to 2, so I know I have just 1 minute till like 10 minutes over. It's over, and then I have 2 minutes for question answer, so I will just take a little bit maybe from the question answer part. So okay, so for algorithms r equal to 2, this is very intuitive. What you do, you split your points into different subsets. So for example, like for r equal to 2, you split your n points into these n over k 2/3 sets of size n to the 1/3 k to the 2/3. Now for each of these sets, you run your one round non-adaptive algorithm. So non-adaptive algorithm clusters whatever the points you have in each set. Then what you do, from each set, you take one cluster representative, and you just build your second level set by taking one cluster representative from the k clusters in this each set. So that gives you some points here, and then you use another round to cluster these points. So the idea is you have this set of n nodes, you split them into subsets. For each subset, you do clustering in one round. For each clustering, you find cluster representative from those subset of elements for each part, and then you club them together and use another round to cluster the representatives. And after that, you just build your cluster based on whatever representative. So if you know these point and this point are in the same cluster, then you know everything here, and everything here is also in the same cluster. Okay, so that's kind of the main idea of the algorithm, and if you do the math, it works out and it gives you that expression. In terms of the lower bound, it's the nice part of this work. I would say that it matches whatever the upper bound you got. The lower bound that we have, it matches exactly. Like when r is a constant, and even when r is not a constant, it's just off by this log n factor. So we have a matching upper bound and the lower bound. And the lower bound, I don't have time to tell you. That's kind of our main contribution. So it uses like Turin's theorem to find out some large, subset of points, which is a large independent set, and utilize that to determine the queries and plant your clusters properly to get this lower bound. So I don't have time to tell you about all of that. And finally, another contribution of this work is like it generalizes to subset queries. And there are notions of strong and weak subsets. Queries, again, I don't have time. You should look into our paper, but there is an interesting fact that shows that when you are asking these subset queries, it just tells you, given a subset of points, how many clusters are there. So that's your weak subset query. And the strong subset query, given a set of points, you ask for the entire clustering of those points. Okay, so strong, it seems like really strong, but what we show that these weak and strong queries, they are nearly equivalent when your sets are not too large. So that's kind of another surprising fact of our work. Okay, so I'm totally out of time, so I'll just stop here.
Thank you very much. Thanks very much for the very nice talk. And apologies for the rush. Everything is very tight. Are there any questions for the speaker before we move on? Any quick question? You need to know K, right? Is there any hope for not needing to know K in your program?
Yeah, so if you're considering the non-adaptive part, you need to know K, but if you're adaptive, then you can find out K, yeah.
Okay, so let's thank the speaker again, and if the next speaker could come up. Okay, our next talk will be towards fair representations, clustering, and consensus.
Okay, so today I am going to present our work. So it's a joint work with my advisor Deeptarka Chakravarti. So he is around. So if you have very difficult questions, you can also ask him. And with other collaborators, Devaruti Das, Tien Long, and Romina. Okay, so what is the clustering? So clustering is basically grouping of data points. So suppose the data points represents students. We would like to suppose group these data points based on their academic performance. So if two students have similar academic performance, we group them together, and if they have different academic performance, we keep them at separate clusters. Okay, but what if like there are 3 input clusterings, one based on academic performance, another based on social behavior, and another based on demographic criteria? In that case, we would like to aggregate all the informations from this clustering and create a consensus clustering. So what is a consensus clustering? Consensus clustering is some clustering where we aggregate the informations from all these 3 input clusterings, like all input clusterings, and create a new clustering. So what does it mean formally? So we are given n clustering, C1, C2, Cn. We call a clustering C as the consensus clustering if it minimizes the L norm of the pairwise distances of this clustering C to all these input clustering C1, C2, Cn. Now, how do we actually measure the distance between two clusterings? So distance between two clusterings, D and C, is the number of pairs UV that are put together in a particular cluster but present like in different clusters. For example, here U and suppose there are 2 data points. So here U and V are present in a particular cluster, but in this clustering U and V are present in different clusters. Hence the distance between these 2 clusterings, D and C, would be 1. So what are the results known for consensus clustering? It is known that consensus clustering is APX hard. There is a very easy algorithm to find a 2 approximation algorithm for consensus clustering. Just among this input clustering, return the best clustering. So simply calculate the L norm from this input cluster and return the best clustering. So that will give you the 2 approximation algorithm. For L equal to 1, that is for the median objective, 11/7 approximation algorithm is known. And for the center objective, that is when L equal to infinity, less than 2 approximation algorithm is known. But the work done until now do not consider fairness in it. So it may happen that the consensus clustering we created, some minority group, maybe some these lower income students, are isolated in that clustering. So how is fairness represented in the literature? So this notion of fairness was first introduced by Chetty, Kumar, Lattanzi, and Vasilevsky in the year 2017. So how do they introduce this notion of fairness? So suppose we are given some set of data points, and these data points are divided into 2 groups. The blue group represents the majority group, and the red group represents the minority group. Suppose the ratio between the 2 groups is P is to Q. We say a clustering is fair if in each cluster of this clustering, this ratio of blue is to Q, blue is to red, is P is to Q, that is maintained in each cluster of this clustering. So what are the related works for this fairness in clustering? So this Chetty, Kumar, Lattanzi, and Vasilevsky has solved this fairness, used this fairness notion to solve K median and K center clustering. And after that, it has been used in several areas, like for correlation clustering and rank aggregation. In our work, it is like very surprising that for a fundamental problem, like for consensus clustering, no one has studied until now this fairness notion. So in our work, in this COL 2025, we study fair consensus clustering. So what do we exactly study? So we are given some set of data points where this blue is to red ratio is P is to Q, and we are also given some set of input clustering. And we want to find the fair consensus clustering. So what do we actually achieve? For 1:1, when the P/Q ratio is 1:1, we get a 3 approximation algorithm. And when the ratio is P/1, we get a 19 approximation algorithm. And when the ratio is P/Q, in general, we get a 35 approximation algorithm. So how do we actually started to solve this problem? So when we started to think about this problem, we started suppose there is only one input clustering. In that case, how do we solve this problem? It turns out that when there is only one input clustering, this problem is actually the closest sphere clustering problem. So what is this closest sphere clustering problem? We are given this, suppose some unfair clustering is given to us, and our goal is to find a fair clustering which is closest to this unfair clustering. And we show that if we can somehow solve this problem, then we can get a 3 approximation algorithm for the fair consensus clustering, even for n input clusterings and for any values of P and Q and for any values of L in this objective. And even if we somehow could not solve this optimal closest sphere, suppose we give an alpha approximation algorithm, then also we can get a 2 plus alpha approximation algorithm for the fair consensus clustering. So yeah, so we actually introduced this problem of closest sphere clustering. We proved that this closest sphere clustering is NP-hard for P not equal to 2. And in our paper, we provide an optimal algorithm for 1:1 case and approximation algorithm for P:1 and P:2 case. Yeah. So how do we get this optimal algorithm? So our algorithm is very simple. So in the 1:1 case, we want equal number of blue points and red points. So what we do is for each of the clusters, we look at what is the number of points extra in that cluster. For example, if you look at this cluster C1, there are 2 blue points and 3 red points. So 1 red point is extra. So what we do is simply cut this extra red point and create, so we get a set of fair clusterings and set of unfair clusterings. And then we merge this set of unfair monochromatic clusterings to get a fair clustering. And we show that this output is one of the optimal solutions. For P:2 case, we proved that the problem is NP-hard. So we give some approximation algorithm. So what we do is we do the 2-step approach. So at first we made this, take this input clustering and make the clustering of in each cluster, the number of blue points would be a multiple of P and the number of red points would be a multiple of Q. And then we take that clustering as input and make it as the ratio between the blue and red as P:2Q. So in the first step, we get a 3.5 approximation for the P:1 case and the 3 approximation for P:1 case in the second step, and 7.5 approximation for P:2Q case in the first step, and again 3 approximation for P:2Q in the second step. So overall, we get 17 approximation for P:1 and 33 approximation for P:2Q. So this is it. So what are the open questions I am interested to solve in? So maybe we can try to solve this closest sphere clustering problem for multiple colors, for overlapping subgroups, or for other notions of fairness that are studied in the literature. So thanks a lot. Merci beaucoup. Yeah.
Thank you very much. Do we have any questions for the speaker? I'll start with a quick question. Do you have any intuition on whether you would, generalize to more than a binary fair feature? Like here you have just blue and red. If it's 3 or 4, is it straightforward? Yeah, is it straightforward?
Yeah,
or is
I
it
think
challenging?
the techniques we used in our paper can be generalized to multiple colors, and yeah.
Probably. Any questions from the audience? Okay, if not, let's ask the next speaker to come forward, and let's thank the speaker again.
Yeah.
The next talk should be Learning Augmented Graph K Clustering. Oh, it's a video? Okay. Okay, it's a video.
Hello everyone. Today I'm learning augmented graph K clustering. This is joint work with Changlin Fan. So let me first explain our problem. The graph K clustering problem is start from edge-weighted graph G. On this graph, the shortest path distance defines the natural metric. And the K clustering problem aims to partition the vertex set into K disjoint clusters. And the objective is to find a set of K centers C that minimize the clustering cost. Clustering cost is defined the sum of connection cost for all points in vertex set V, and the connection cost is defined as just the q's power of the distance for each point and the nearest center among C. One can find that this generalizes the well-known k-means problem when q equals to 2, and also k-median problem when q equals to 1. There are many known algorithmic results and hardness results about k-clustering problem. So for example, k-means problem, there are many constant factor algorithms and there are also many hardness results. One of them is assuming some hypothesis named Johnson coverage hypothesis, and it says it is hard to approximate like better than 3.94 in error metric and 1.73 in error metrics. But the point is that even we assume some hypothesis, the huge gap remains between upper and lower bounds. So this situation motivates the need for new framework to address these challenges to solve K-clustering problem. And learning augmented algorithm is one of them. It is also known as algorithms with predictions. Basically, learning augmented algorithm is a new framework for achieving the performance beyond worst case bounds. So it leverages predictions from a machine learning model, which can be treated as an oracle, where it should not be a machine learning model, but it can also be like heuristic strategies or just another classical algorithm. And for learning augmented algorithms, usually they have two key goals, which is consistency and robustness. For first one, it means that with high quality predictions, the algorithm should significantly outperform classical ones. And for second one, with low quality predictions, which is like equivalent to just a random guess, the algorithm's performance should be comparable to classical ones. So we use learning augmented algorithms, which means we define some prediction model to solve K-clustering problem to achieve better approximation quality in polynomial time. So here's the definition. Let the optimal clustering for a K-clustering instance be a P star, which is P1 star to the Pk star. Pi star means the ith optimal cluster in the optimal solution. And a predictor named pi, it can be viewed as just a function from the vertex set to the k integer set. It means that predictor assigns a cluster label to each vertex. And let pi be the set of points labeled I by the predictor. Then we can define the performance of predictor now. So we say predictor phi has a label error rate alpha if for all clusters, the size of the intersection between pi and pi star is not less than 1 minus alpha times the maximum value of the size of pi and pi star. So intuitively, it means that our predictor correctly labeled at least 1 minus alpha fraction of all vertex set. There were many prior works used a similar prediction model to solve the k-means problem. One of the best known results is a deterministic 1 plus 7.7 alpha approximation algorithm. And furthermore, one of the paper provided empirical results which suggest that such predictors phi are practical to implement. However, all those prior works are only work in Euclidean spaces. So our key question is to resolve that limitation. So can you cluster effectively without geometry? So, and now here's our results. First, our result is algorithmic result, which means we devise a new approximation algorithms that achieves 1 plus order of alpha to the 1 over q for k clustering problem on general metrics. We note two things about our algorithm, which is the first, our algorithm achieves consistency, and second, our algorithm requires no minimum cluster size constraints. Also, we achieve the hardness result in terms of query complexity, but I will explain it later. And let me explain a high-level idea for the k-means problem. Before that, we just introduced two new notations for this. So cost xp means the cost of assigning points in a set X to a center P. And also, we call Cx be the optimal center for a set of points X. And here's our algorithm. So for each predicted cluster Pi, we are going to find a subset Bi of Pi, which we called core subset. Bi has a size of 1 minus alpha times the size of Pi, and also Bi, we are going to choose Bi, which has the minimum internal cost. And the algorithm is simple. We perform these steps for all k clusters P1 to the Pk and just output k centers CB1 to the CBk. To understand why this logic is effective, we first introduce some lemma. So let's say for any point set X, let P be a subset of X with consisting the major part of X. Then we can prove that the clustering cost of X when center is a CP is not that worse compared to the optimal clustering cost for X. And then the picture shows our situation. So basically, our proof consists of two steps. First, we starting from the optimal clustering of P star, which means the center is at the CP star, we are going to first move the centers from CP star to the CP intersection P star. Because P intersection P star is already the major part of P star. And also, from the definition of predictor error rate and the definition of how we compute the subset B, we can claim that B is also consisting major part of P star, while B is not totally included in P star. So the second step of our proof is that to move the center CP intersection P star to the CB. From those two steps, we apply the above lemma to just get only small multiplicative error in terms of approximation quality. Then we can intuitively understand that our logic effectively removes potential outliers. And let me explain the query complexity hardness results. First, we define query complexity as the number of labels requested from the predictor oracle. One of the prior works showed that if we assume exponential time hypothesis is true and to achieve 1 plus order of alpha approximation, then it is impossible with an algorithm that makes at most the sublinear number of queries. So we extend this hardness result to our k clustering problem using a similar proof structure. Since the point is our algorithmic result, so I will just briefly explain the proof. So in the prior work, they start from the ETH. They use the reduction from ETH to minimum vertex cover on 4 regular graphs. They also applied the reduction from the vertex cover to the k-means, and finally show that each query to the k-means predictor reveals the information about the optimal vertex cover due to the structure of the second step, reduction. And here's the difference. The point is we devise a new reduction from minimum vertex cover to k clustering problem. And also we devise new proof for the third step too. And yeah, that's it. This was our presentation, and thank you for listening. Hello, everyone. Today I'm going to talk about learning augmented graph K clustering. This is joint work with Changling Fan.
So I was just told that the speaker is on Zoom, or
Yes, it's on Zoom.
are there any
Thanks,
questions? Are there any questions from the audience?
yeah.
Anyone?
Any questions, sir?
It seems like there are no questions, so we'll move on to the. So let's thank the speaker again now that he's here, actually. And the next speaker will set up. So the next talk will be on estimating stationary mass frequency by frequency.
So I'll start. So spoiler, this is not about clustering. So today I'll be talking about this joint work with my co-advisors Vidya Muthukumar and Ashwin Pananjadi. Vidya is around. So we'll look at the discrete distribution estimation problem from dependent samples. So this has applications in DNA sequencing as well as natural language modeling, where you want to estimate these kinds of distributions over the words and DNA, protein foldings. So we'll focus on the large alphabet regime where the number of samples are much larger than the number of symbols are much larger than the number of samples. We'll start by understanding the existing results in the IID setting, and then our goal would be to design a universally consistent estimator when the data is dependent. So what is dependent data? So we'll assume that we are given a single trajectory from a stochastic ergodic process. So this has certain correlations in between them. Pi represents the stationary distribution of this process, and X is the sample space. So in order to deal with the correlations, we assume that our process is exponentially mixing. So we define this coefficient alpha tau, which captures the correlation between things which are separated by this tau factor, and we assume that this correlation decays exponentially with time. And this is the mixing time definition. So essentially, mixing time you can look at as how many time steps you require to get like a sample from the stationary distribution. So this is actually a practical modeling choice because a lot of finite state Markov chains, some hidden Markov models, as well as duplicated sequences, we'll see later, satisfy this mixing condition. So we'll do the estimation in a frequency by frequency sense, where our aim is to estimate this quantity which we call the vector of count probabilities. So here zeta represents the frequencies of the different symbols. So for each frequency, m pi zeta collects together the stationary mass of symbols that appear zeta times. So it goes through the entire sequence, it finds out which symbols appear a particular number of times, and for symbols that appear equal number of times, it collects together their stationary masses. So one interesting point is that m pi zeta is actually random because it depends on the actual symbols that I see, and also it has information about the underlying distribution, pi, which we are trying to estimate. So we'll understand this by an example. Suppose we are given this symbol space with certain stationary masses. This is the sample that I observe. So we'll use phi of zeta to represent the number of symbols that appear with frequency zeta. So in this example, phi of 0 is 1 because D is not observed. Phi of 1 is 0 because no symbol appears once. Phi of 2 is 2 because both P and C appear twice in this example. Therefore, phi of 2 is 2 and phi of 3 is 1 corresponding to A. So in order to calculate the vector of count probabilities, we'll go through it and we'll collect together the stationary masses of symbols that appear same number of times. So the first element is m pi 0, or the stationary mass of things which are not seen, and this corresponds to the symbol D in our case. So this is pi of D. M pi of 1 is 0, and m pi of 2 corresponds to the stationary mass of both P and C. So this is pi of B plus pi of C, and this is similarly pi of A. So our goal would be to design an estimator which takes as input the sequence and gives me a probability simplex over this frequencies. And we'll do the estimation in the total variation distance. So, and how does this estimator relate to the distribution estimation problem that we saw earlier. So we can use this m hat to get an estimator for the probability masses as well. So what we could do is we divide the m hat zeta equally among all symbols that appear zeta times using this formula. So such estimators which assign equal probability to symbols that appear equal times are called natural estimators, and these form a benchmark for comparison in this setting. So in this lemma, we established that our estimator that we get from dividing this mass equally is actually competitive with the respect to the class of all natural estimators, and this class will contain the estimator which has exact knowledge for pi, but it is constrained to be a natural estimator. So we'll first look at the IID setting. Here, the data is IID from pi. The correlation coefficient is 0, and the mixing time that we saw earlier is simply 1 because of independence. So one approach we could take is using the empirical estimation, which assigns probabilities just based on the frequencies. However, this fails in the large alphabet regime because as you can see that in the large alphabet regime, a lot of the things will not be seen. So the missing mass would be very high, the m-pi0 quantity. But empirical estimator would assign 0 probability to unseen things. So in high dimensional regimes, empirical estimator fails. So there are a lot of techniques which are used to avoid assigning 0 probabilities to things that are not seen. So we call these the smoothing techniques, which add constant frequencies to all the things and then normalize it to get the final distribution. So there's another technique which is usually good, which is the hybrid estimation, where for low frequencies, we use this good Turing estimator, and for large frequencies, we use the empirical or the plug-in estimator. So we'll look at what the good Turing estimator is. So in 1953, Good proposed that instead of using for estimating stationary mass of m hat zeta, I'll use symbols or proportion of symbols that appear zeta plus 1 times. So for missing mass, instead of using symbols that appear 0 times, use the frequency of symbols that appear once. This is based on the observation that m pi zeta is approximately equals to this. So the good Turing estimator is approximately unbiased. So we'll understand the good Turing estimator via an example for missing mass. So for zeta is equals to 0, this good Turing has a very good leave one out interpretation. So what it does is it goes through the entire sequence, leaves each symbol out, and calculates these indicator random variables over the rest of the sequence. So for example, for I equals to 1, it will leave out the blue symbol, and it will calculate the indicator or find whether the blue symbol appears in the rest of the sequence. So, and it will add it if the indicator is 1. So essentially for I is equals to 2, I equals to 4, similarly, and I equals the orange quantity as well is good. So this leave one out interpretation will be important as we go forward. So however, most of the estimators that we see were originally designed for IID sequences, and they're not equipped with handling dependent data. We'll show this via this simulation where we generate a base IID sequence. And in order to induce correlations, we duplicate each symbol a certain number of random times, which is given by a geometric random quantity. So this essentially creates a sticky Markov chain where the mixing type is proportional to n naught raised to 0.2. So in this setting, we see that the TV distance between the actual and the estimated quantities is pretty high. For the uniform distribution, we even don't get consistent estimation. So what are the difficulties of handling dependent data? The first is temporal dependence, which induces a certain bias in the problem. So Chandra et al. Established that if I use the good Turing estimator from before directly on Markovian sequences, it suffers from a non-vanishing bias. And recently there was a work by Pananjudi et al. That proposed an estimator for missing mass for Markovian sequences. The question that I try to answer is it possible to use the recent developments in order to perform consistent distribution estimation for like mixing sequences which satisfy the exponential condition that we saw earlier? So we'll first look at the windowed good Turing, which was proposed for missing mass. So we'll recall the leave one out interpretation of the good Turing, where it goes to the sequence, leaves one symbol out. So in order to decouple the random variables, instead of leaving one symbol out, what we could do is we could leave all the things that are dependent on the current symbol. So essentially what this winged does is it uses the good Turing but with a windowing approach. So we'll understand this by an example here. So earlier we saw that good Turing was leaving just a single symbol out. So for each I, windowed good Turing forms a window around the current symbol, and all the things which are outside this window are supposed to be approximately independent because of the mixing condition that we had assumed earlier. So for each thing, for each I, it goes through the entire sequence, leaves a window out, and computes the indicator random variables. So what is the estimator we propose for mixing sequences? So we propose a hybrid estimation approach where for low frequencies, we'll use the Wingate estimator, which, and for large frequencies, we'll use the plugin or the empirical estimator, and both these are implementable in linear time. So for mixing sequences, we derive this theorem where if I choose the transition point between the Wingate to the plugin estimator of the order n raised to 1 by 3, then the TV distance between the m pi and m hat decays as this, where compared to the IID case, we are having to pay this extra factor of square root t mix because of the correlations in the data. So essentially, using this hybrid estimation technique, we are able to perform consistent estimation, and the result does not depend on the underlying size of the alphabet at all. We are able to recover the IID results as well, and we do not, by setting the window size as 1, and we also don't require Poissonization, which is a widely used technique in the IID analysis to make the multiplicities of symbols independent of one another. We provide new analysis for both the small frequency as well as the large frequency errors. For small frequencies, we give an adaptive analysis which adjusts the properties of the underlying stationary distribution. For large frequency errors, we provide a concentration inequality for these exponentially alpha mixing sequences. So this shows that our estimator performs much better on the mixing sequences that we say. So key takeaways are that we looked at the discrete distribution estimation problem for dependent data. We proposed a hybrid estimator which uses the complementary strengths of the Wingate as well as the plugin estimator. We are able to derive a result which is independent of the size of the alphabet. What are the future directions? So what do minimax estimators look like in this dependent data regime? And can we go beyond TV distance to other forms of divergences? So yeah, thank you.
Thank you very much. Are there any questions from the audience? Any questions for the speaker? No questions. Okay, so if not, let's thank the speaker again, and then I'll ask the last speaker to come up. So our last talk will be on metric clustering and graph optimization problems using weak comparison oracles.
Okay, so thank you. So my name is Shamantak, the third name that you see on this slide. So this is joint work with Rahul, who is a PhD student at Duke, Wenji, a PhD student at Cornell, Sayam, who is a faculty at Cornell, and Stavros, who is a faculty at U Chicago. So ideally, Rahul should have given this talk, but unfortunately, he couldn't make it. So I'm just filling up. Okay, so we are back to clustering. Okay, so I think all of us by now know what K-clustering is. We are given a bunch of points, and I assume they're embedded in some sort of metric space for the purpose of this talk. And our goal is to partition them into various clusters. And as most of us are aware of, what are the most popular objectives of clustering? Well, you can optimize K-center, you can optimize K-median, you can optimize K-means. They all sort of trade off various aspects of clustering, depending on the application. But one recurrent thing which is sort of inherent in all of these problems is that each of these questions, they inherently, when you design an algorithm in a classical computation, you inherently assume that you have access to distances, right? Or pairwise distances between points. But this poses significant challenge. And the reason is that, think of handling some image data or text data. So it's often very hard to come up with a notion of distance between them which is semantically consistent, right? And even if you can use some complex embedding models to do that, it's often computationally expensive to compute such distances. So what's the solution? Can we do something else? So this has already been sort of pointed to by Barna in her talk, which was the first talk of this session, that you can consider what is known as an oracle model and assume that the oracle answers sort of simpler questions. So what could be simpler questions? I'll come to that in a minute. But the main intuition behind our oracle model is that comparing is easier than computation. Okay? So, for instance, if you look at this picture and if I ask you, okay, is picture A closer to picture B or is picture C closer to picture D? I think all of us will agree on the answer. Yeah? It turns out that you can even train machine learning models, not in a not very expensive way, to answer such queries. Okay? So given 4 points, you can ask, is A, B closer to each other or C and D are closer to each other? Okay? But of course, it comes with caveats. They provide limited information, they can have noises, so we have to address all of that in our model. And of course, as a second model, you can consider the traditional distance query model, which is you give a pair of points and you ask, hey, what is the distance between these two? Okay? So in our work, we essentially use a combination of both these kind of queries. But before going into the results, I need to define one more thing, which is how do we really model the noise in our so-called quadruplet queries? Okay? So one is what we call the probabilistic noise model, which is exactly what it says. So with a constant probability, it will give you the right answer. With the remaining probability, it can be wrong. And there are two important features of the probabilistic model. One is they're independent across different queries. And second is persistence. So if you keep asking the same query multiple times, the answer won't change. So with the same probability, it will keep giving the wrong answer or right answer, whatever. Yeah? The other noise model that we consider is what is known as adversarial noise, which kind of says that, okay, think of like two pairs of points. Now, if the relative distances, the distance values are very close to each other, then this oracle can give wrong answers adversarially. But if they are far apart, then they can provide the correct answer. They will provide correct answer. Okay? This is a slightly easier model in some sense, as we will see, but yeah. Okay, but for the purpose of this talk, I will mostly focus on the probabilistic noise model because that's more interesting and challenging, somewhat more practical. Okay, so let me tell you a bit about the history of this model. So it was introduced by a paper, through a paper by Adhanki Galhotra and Barna back in 2021. And they solved the k-center problem by using only about order nk square many queries. But their result only holds in the adversarial noise model, not really in the probabilistic noise model. For that result, they need some inherent assumptions that the underlying clusters are somewhat large and so on and so forth. Okay, this year in pods, in fact, this paper was presented just a week ago in Berlin. A subset of my co-authors, they introduced this so-called rank measure model, which has both the quadruplet queries as well as the distance queries. And they could solve all the three clustering problems, k-median, k-means, and k-center, using about nk many weak quadruplet queries and about k-square many strong queries. Okay? And they also showed that this is necessary. You cannot solve k-means or k-median. You can solve k-center, by the way, but you cannot solve k-means and k-medians without using this additional number of strong queries. Ideally, we would have liked to avoid those, but you need to use a few of them. Okay? There's a slightly different model which also appeared in last year Colt by this paper by Bateni and all. So what they say is that, okay, their oracle is somewhat different. They said that, okay, if you can ask the distance between a pair of points, but the oracle can simply give an arbitrarily bad answer with a constant probability. Okay? So then they don't do this relative sort of comparison as we do, as our oracle does, but yeah. But it's somewhat related to what we are doing here. Okay, so what are our contributions? Now, if you think back, this is well known that even in the classical setting, right, when you assume that you have access to all distances, it's well known that for solving any K clustering problems, you need kind of NK many queries. Okay, you need NK many accesses to distances. You cannot really beat this bound. It's a barrier. So the question we ask is, can these strong queries, which is required, be completely replaced by this weak quadruplet comparison oracle? Okay, under the probabilistic noisy setting. Now it turns out that you cannot do that. Yeah, that's what they show in this Pod's paper. But what we are able to show now is that you can do with NK many quadruplet queries, provided that you use a few additional strong distance queries. Okay, so you need to know a few correct distances, otherwise you cannot really do anything. So, okay, so whenever I write tilde, it means I am hiding like logarithmic factors. Okay? All right, so that's the first contribution. In the second contribution, we considered some special metric spaces which often appear in practice. So these are metric spaces with so-called low intrinsic dimension. For all practical purposes, think of low dimensional Euclidean spaces, although this is slightly more general, significantly more general actually. The question is, under this setting, can we actually break this NK barrier or not? Okay? Because it can be done in the classical setting. It turns out that we can, okay? And this is probably the most surprising result in our paper, that we need n plus k square many queries now, in addition, again, to a few strong oracle queries. And this really breaks this nk lower bound, which you cannot beat in the general metric spaces, okay? So that's kind of surprising and interesting. And finally, we consider a more sort of much more general question, which is that, is there a possibility that you can actually learn the entire metric space itself, okay, by just having access to these weak comparison queries? Okay? It turns out that you can do it approximately under the assumption that your metric has this, again, low intrinsic dimension property, and also sort of the spread is polynomial. Okay? And sort of you can learn the distances approximately, so now you can pretty much solve any problem that requires distance access, like minimum spanning trees, whatever, minimum cost matchings, and so on. All right. Okay, so let me just spend like a couple of minutes on the K-center problem under the assumption of low intrinsic dimension, which is perhaps the most interesting result in our paper. Okay, so here is one way to solve the K-center problem. Okay, so you are given a bunch of points. How do we solve K-center? Here is one way. You sample uniformly at random roughly k log n many points, okay? And you compute a K-center solution on them, maybe within a constant factor approximation, that's fine. Now what you do is you identify points from the remaining set, those points which are another constant factor away from this set of centers that you have just computed. So let us just call them the good points, okay? So now what you do is you sort of discard all the good points, okay? And you just recurse on the remaining points. The question is, for how many phases do you need to do this? It turns out that there is a property which has been well known by now, that about a constant fraction of the points would be good, so you only need about log n many rounds, right? So at the end, you just output all the points that you have sampled, which is also known as a coarse set. You solve the K-center on the coarse set, and you are done. Okay? Now here is our key technical contribution. So remember, we have to, essentially, this algorithm involves two different things, right? One is solving this so-called local K-center problems on these sampled points. So that we show how to do using about O tilde of k square many queries and constantly many distance queries. Okay, constant modulo the tilde. The other very important part is, once you have this local K-center, how do you identify these so-called good vertices? Yeah? And this turned out to be significantly challenging, and here is exactly where, in fact, this is the only place where we use that the inherent metric is of low intrinsic dimension. And we could design an algorithm which utilizes only about O tilde of n many queries. Okay? Right. So I will just skip the details of this algorithm, and because I just have a minute left, so I will quickly skip to future work. So as far as I see, there are three interesting questions that one can look into. So first of all, we do k-center, k-median, and k-means, kind of up to optimality. I mean, as far as the number of queries is concerned. But there are these exotic clustering problems that people have looked into in the recent years, fair clustering, or you can also try to sort of optimize a very general norm of the cost vector. So what about those? Can we also extend this query model to those problems? What about other settings like ranking? Yeah, so those of you who are aware of the ranking problem, you are given a bunch of ranks and you want to do something about them. What if these ranks are false? I mean, not completely correct. They can be wrong with certain probability and so on and so forth. So can you do something there? And the other interesting direction could be, remember, we had assumed that our error probabilities are independent across queries. And it turns out this is also not very practical, because two different queries might have some correlation. So can you model this correlation somehow, and can you, come up with some interesting results there? So I think I would just stop there. Thanks for listening, and I'm happy to take questions.
Thank you very much. Are there any questions from the audience for the speaker? Anyone? If not, I have a question. So can you say a bit more about what notion of low intrinsic dimension do you use, and how does it go into the result?
Right, exactly. So that was this slide. Okay, so low intrinsic dimension. So the property that we used is basically that if you have, let's say, so you have a metric space, and let's say you have a ball of radius r, then you can cover all the points inside this ball with about a constant number of balls of half the radii. So this allows you to build a data structure which is known as ring separator trees. So we show how to build that using few queries. So that's the main contribution, I would say.
Okay, nice.
Yeah.
Thank you. Any other questions? If not, then let's thank this speaker and all the speakers of this session again. And I think now we have a coffee break for half an hour, and then there's going to be another short session, and then invite a talk.